Hello, my name is Chris, um, and this is my the Project One assignment. The title of it is Relative CPU Performance Statistics by yours truly, Christopher Angulo. Um, so, this is today's date, November 19, 2023. Um, so, to go into some background information of the dataset I used, I pulled it from the UC Irvine Machine Learning Repository. The name of the dataset is called Computer Hardware. It's an older dataset from 1987. It's basically information about CPU hardware factors. For example, it's minimum memory channels, maximum memory channels, cache memory, machine time, clock cycle, the brand of the CPU, and then some performance scores. There is a published relative performance score and an estimated relative performance score. Uh, Relative in regards to with a CPU performance score, it'll be based off uh, like one main CPU, and then the scores of other CPUs are relative to that one. Um, so to get started, the analysis practice, more analysis background information. As I mentioned, here I'm just mentioning that there's 30 different CPU manufacturers in this data set, 209 total rows in the data, so 209 CPU observations. We went over the factors, the variables that are explored in this data set. So I'm going to begin this analysis by observing the relationship between the estimated relative performance and the PRP, which is the published relative performance. Um, so estimated is a relative performance of the CPU that was done through another study cited here, that tries to estimate the relative performance of a CPU theoretically, and then a published relative performance of the CPU is the actual testing of the CPU. So the reason I want to test out if there is a significant relationship between these two scores, because if there is, then that means that we can use an estimated we can use the method used in this study to get the estimated relative performance. We can use that to be able to estimate the relative performance of future CPUs if there is not enough resources to conduct, the real published relative performance, the actual test of the CPUs. So we can calculate. So first, here's just a histogram of the estimated relative performance. 15 bins is the best amount of bins for this, just based off on using the square root of n, so the square root of the number of rows. But you can switch it, and this is just to get an idea of the distribution of the estimated relative performance. And then we do the same thing for the published relative performance. And it's just to give us an idea to see if they have some similarities, even though they're not graphed on the same histogram. Just, you know, they do seem to be both our right skewed distributions. So that kind of tells us that since both of them are very similar in that shape, maybe there's a possibility that there is a great correlation between the estimated relative performance and published relative performance. So then the next thing that we do is plot a linear regression model between the ERP and the PRP scores. And the objective of this model, again, is just to see if there's a correlation between these two. So here we have this interactive plot. It lets us adjust the confidence level. We're doing linear regression here. And this is what our linear regression looks like. And you can kind of play around with the confidence level. Usually standard is 95. So then we go to the next step in the linear regression model, we want to determine if this linear regression model is good or not. We want to prove it to be a good fit to award it its predictive significance. So to test for the verification of an adequate linear regression model, we need to perform these. We need to perform verification for these three main assumptions. The first one is that the errors are random variables with mean equal or close to zero. So the errors of the linear regression system. That the errors have a constant variance, and that the errors are normally distributed. So for the first assumption, we can verify this through computing the mean of residuals and seeing that this mean is very close to zero or actually zero. And for the next two assumptions, we can verify them by examining a plot of residuals of the errors. And to be able to meet this criteria, this plot of residuals needs to at least visually appear as random scattering above and below zero. So for assumption 1, we go ahead and compute the residual mean, and it's this very small number, which is pretty close to zero, so we're going to say that assumption 1 passes. For assumption 2 and 3, we're going to go ahead and plot the residuals of the linear regression model and check for that scattering, see how it's distributed. And what we see here is that it's not very random. We see that at the beginning it's very concentrated, the residuals, and then as we go out at the beginning of the x-axis, as we go further along the x-axis, we lose a lot of this density here. So what that tells us is that assumptions 2 and 3 fail. It's not very random. They're all concentrated here. So although the linear model passes assumptions 1, assumptions 2 and 3 do not seem to pass by visual analysis of the residuals plot. So what can we conclude from this? Well, we can at least say that this is not a very good linear regression model. And this can also mean that the ERP is actually not a very good way to determine a PRP, to kind of predict the PRP score based on an ERP score. Or it can also mean that we just need a better model, or we need more data, or there are just other variables that are more important than it's a multivariable type of linear regression. But at least we're kind of seeing that it's not solely that this ERP is not very good at determining that PRP. Now we do a different analysis. We're gonna analyze the PRP versus the CPU cache. So here we're trying to find a relationship between, again, this the cache size of the CPU and the PRP score of the CPU. Now maybe it's not mainstream information, but usually if a CPU has good performance, the higher the performance of the CPU, it probably has more cache. But there's a limit to how much cache memory you can have. If you start to have too much cache, it actually starts slowing down the system. So we want to see how these two compare, what relationship they have. So first we just look at a general scatter plot. This is again, we want to focus in this next part of our study here between cache memory and PRP. But this is an interactive plot where we're gonna have cache memory stay as the x-axis, but the y-axis is variable, so you can play around with it. Switch it to minimum memory channel, a machine time cycle, and it'll give you that scatter plot between these. And then the color of each data point is just the brand. So if you want to focus on a certain brand of CPUs in the data set, you can just blur others out. But yeah, if we go back to the PRP, this is what it looks like. So it just kind of gives us an idea of how that data interacts with one another. Um, Now here we're gonna do a linear regression model as well for CPU cache size and the CPU's PRP score, just like we did with the previous two variables. Um, and yeah, so then this next slide is gonna contain another graph of CPU cache versus PRP, but this one is not a scatter plot. This one is a linear regression model for these two variables. Starts up with a 95% confidence interval, so we see that the linear model is this blue line here. So it's a little, confidence interval is a little wide. And I also added other models, other statistical models to see if, just visually see if maybe another model probably makes more sense, which is probably the case in this data. But it just lets you kind of take a look at this. So we go to the next slide, and now it's based on the linear regression analysis and the CPU cache versus the PRP. So again, we want to determine if this is a good linear regression model or not for these two variables, the cache size and the PRP. We're gonna base it off. We're gonna base if this isn't a good linear regression model based on the same three assumptions as we did with the previous two variables. Check if the random variables have a mean that's very close to 0 or equal to 0. Check if the errors have a constant variance or errors are normally distributed. So for these two variables with their linear regression model, we see that the residual mean is also very close to 0. This is a very small exponent, right? It's going to have 14 zeros after the decimal place. So we say that assumption 1 passes. Now we're going to take a look at assumption 2 and 3 and analyze it through the residuals plot of this linear regression model. So here's the residuals plot, and we have, again, just like in the other linear regression model, a high concentration here to the left. So that means it's not a good linear regression model. So the agglomeration of residuals to the left of the x-axis on the residuals plot above indicates that the assumption of a constant variance is invalid. This means that assumptions 2 and 3 fail. So this is not a significant linear regression model. So what does this mean? What can we translate this to? Well, we could probably say that the CPU cache size and then that the CPU PRP score, the published relative performance score, doesn't have a very good at least linear regression. One possible thing could be that CPU cache, is only one of many factors that affect the relative performance score of a CPU. So maybe that it just doesn't hold enough significance in and of itself, the cache size, to boost up the performance of a CPU. Another possibility is that there's just maybe a better model to create the relationship between these two characteristics, that we need more data. And again, this is my bibliography where I got the data from the UCI machine learning repository. And that concludes my presentation of relative CPU performance statistics. Thank you.